All right, so this is the lecture number 2 on the Bayesian inference of epsilon machines, work that I'm doing here with Jim as a postdoc. And I'm going to start off just again with the overview of what we did sort of last time, which was from the basics of statistical inference, a very quick introduction to Bayesian inference, and I think I will mention a few points on that again to try and get a better sense for people of what exactly is happening there. And then we went through a couple of examples, the biased coin, inferring the transition probabilities, moved to unifilar HMMs, and looked at the EvenOdd process in particular. And we used the topology. We knew what the edges were. We knew what symbols they output. And so all we were doing here was inferring the transition probabilities. And one of the important parts of that was that we also had to assume a start state to do this, because if we assume a start state in a unifilar HMM, then there's a unique path through it, and that allowed us to count edges. And so that was an important thing that allowed us to connect sort of very traditional statistical inference to something where the states are hidden, and it's because we assumed start states. And so this was all for fixed topology, and now we're going to move into, we have one data set, and we have a whole bunch of different topologies. How do we decide which one's best? So that's today. And part of what we'll be doing is using an enumeration algorithm by Ben Johnson, one of Jim's grad students, on how to enumerate, in particular, topological epsilon machines. So that will be one type of candidate structures that we can look at. And so we'll do an example again with the EvenOdd process, but this time we won't assume that we actually know the structure. We'll figure it out from this library. And then I'll show some plots that have sort of more data and better ways of looking at things from the golden mean, the even, and the simple non-unifilar source, which of course we can't directly infer this because it's not unifilar, but we can still use unifilar representations to estimate these things. So that's part of the interest. This is an out-of-class example in terms of inference. And I'll end up with more general out-of-class example and one of a non-stationary process. So kind of cautionary tales of if you deal with real data and you don't know what it's coming from, what might you expect and how much should you be worried? And again, I'll be doing coding examples, and there is a Sage workbook up there that does all of these things. So most of the coding examples you can go and play around. So there's two notebooks. There's one for the previous lecture, and then there's a new one now that does all this stuff. So pretty much all the computation is available for you to play around with. So this is the one slide review of last time. And I guess talking with Jim afterwards, one of the things I wanted to sort of emphasize is this idea in Bayesian statistical inference of starting off with a prior distribution and going to a posterior distribution. And in the last lecture, we did this on 2 levels. So in this first one, we were inferring transition probabilities, and so we had a distribution over transition probabilities, assuming a start state and assuming a topology, but it wasn't informed by the data. We wrote down a likelihood, and sort of the combination of these two things are reweighted, and it gives us an updated distribution over parameters that now takes into account the data. And in particular for this part here, because these parameters are transition probabilities, these are continuous parameters, we had a special form here called a conjugate prior. So if you had a conjugate prior, it meant that in this case we would have a beta distribution or a Dirichlet distribution. We would end up with a beta or a Dirichlet distribution over here. But these two things are very, very similar. Okay? And so it's always this kind of thing where you're starting off with a prior distribution and you're moving to a posterior distribution. And the same kind of thing here, we did this extra level where we wanted to, after having the transition probabilities, we wanted to know what was the actual start state, because we weren't interested in that necessarily. We wanted to figure out what that was given the data, and it's the exact same thing here, where now we have the probability of each start state, and our prior there was to assume that each of the start states was equally probable. So if there's 5 states, it was 1/5 a priori, but then we had the evidence that actually came from here. So there's these connections between the different levels, goes from here to here, and that tells us how likely each of the start states is given the data. But there's always this process of a prior distribution to a posterior distribution. And here there's some model that's telling us how to evaluate different parameter settings. So that's the very, very high level. And this idea of updating distributions based on data. Okay. And the particulars of the mathematics are, depend on what model you're looking at. We're looking at hidden Markov models or Markov chain-like things. But you could do the exact same kind of thing for inferring the mean and the variance of a Gaussian distribution, where you'd have priors and posteriors. And the mechanisms would be very, very similar. All right. So hopefully that is a little bit more clear. But I really encourage that if this is novel to you, actually just look at Wikipedia for Dirichlet distribution. Look at Bayes' theorem and just grind through the mathematics of one example, like by hand. So some of these things in particular, when there's conjugate priors like we have here, you can actually calculate these things and take a prior distribution, modify it with a likelihood, and calculate them out. And it's a useful exercise. It's not always fun, but it's useful and it's convincing, especially if it's unfamiliar. Okay, so we're going to infer structure now. And so one thing that I wanted to do was to sort of contrast what I'm going to be doing with what is more common, probably. And you're more likely to have encountered this kind of thing. So this is very generally, and I'm sure there are exceptions, but often when people say that they're inferring hidden Markov models, they're usually assuming some sort of fixed topology that they've assumed. It's a certain number of states, certain number of connections, the outputs are of certain types. And they're often considering non-unifilar topologies. So there isn't a unique start or a unique path given a start state through these things. And as a result, you end up with a whole class of algorithms that numerically optimize the transition probabilities to agree with the observed data. And so these are called expectation maximization algorithms like Baum-Welch. And this comes up in statistics all the time for when you have some sort of a hidden state thing that you're trying to infer. And here it's really you have to optimize over all the possible paths. And there isn't a unique path for an observed data set. There's many, many paths. So there's this numerical optimization. But the main thing is that they are considering non-unifilar topologies, and they're usually assuming a single and fixed topology. And so what we're going to do differently is, because we're interested in epsilon machines and epsilon machine-like things, we're restricting to unifilar hidden Markov models. So we're going to only consider those types, and we're going to use model comparison to infer topology. So we'll have a whole set of them. In this case, we'll be looking at, in most of the examples, on the order of 1,400 topologies, and say, given a data set, which of these is the most likely? And we'll provide a distribution. We could take into account the uncertainty in the structure in the same way we did the uncertainty in the start state and the transition probabilities that we did last time. So the sampling that we did to estimate like entropy rates and C mu, to get a mean and credible intervals, we could do the same thing for structure. Okay, and potentially we could consider this a different way of thinking about structural inference. On another level, it is very conventional Bayesian application of these ideas. I've been doing basically just model comparison on various levels. And so the next thing is, what set of models should we use? And so I'm going to use one in particular, but it doesn't have to be this one. But it's certainly a good one, and especially if we're interested in epsilon machines, it's a good place to start. It just has to be unifilar HMMs can be fed into this. So we're going to look at topological epsilon machines, and I'll go through definitions in just a minute. But the motivation for this is that there was hard work by Ben Johnson in this paper here to figure out a fast way to calculate every 1-state, 2-state, 3-state, 4-state machine for a given alphabet size. And that's actually not such a trivial thing to do. So we're going to take advantage of this and be kind of brute force about it. Just say, we'll look at everything we can up to a certain number of states. And so that will be our set of candidate topologies. And really, we're limited by time and computational resources. So one thing you'll see is that as you get more and more states, the number of topologies that are available grow very, very fast. And so you can only do this within limits. So in the long run, having a maybe more creative way to choose sets of models to look at would be a good thing. But this is a good place to start and quite interesting already. So definitions, again, a couple of these we saw from last time, but to get us all on the same page, finite state edge-labeled hidden Markov model has our set of states, a finite alphabet, and the set of symbol-labeled transition matrices, stuff that you're all familiar with from the class. And if you want the state-to-state transition matrix, we can sum over these things and get a T that's independent of the output symbols. We can further refine this to what a finite state epsilon machine is by the additional restrictions that they have to be unifilar. So for each state and each symbol, there's at most one outgoing edge from state sigma I to, and has output symbol X. And again, for the inference, this is really, really critical. Like, this is the reason I'm able to do the edge counting and why what I'm doing applies to the epsilon machine structures and not generally to hidden Markov models. And then for an epsilon machine, of course, each state has to be probabilistically distinct, and that there's some word that has different probabilities for each pair of states in the machine. Okay, and then something we didn't talk about last time is topological epsilon machines. And so part of the way that these are enumerated is to look at the topologies in a very particular way. And so the definition here is a topological epsilon machine is a finite state epsilon machine where the transition probabilities for each state are equal on all outgoing edges. And so I gave just two examples here of how this creates restrictions on what types of topologies you'll see in this set. So one example here is this one. So the way that the probabilities are set is you have this state and there's an edge going out this way, an edge going out that way. They have different symbols, so it's unifilar, but they're set equal to 1/2, 1/2. So that's, each state is equal probable. Here, there's only one, so it's set to probability 1. And so this would be a valid topological epsilon machine. Whereas this one would not, because we have 1/2, 1/2 going out here, and then 1/2, 1/2 going out here, and these are not probabilistically distinct. So even though in inference, we're going to be sort of ignoring the transition probabilities and inferring them, the set of topological epsilon machines in the way that the enumeration algorithm works is a test for this. And so that's one thing that's important to take into account. So for example, if you have something that has a support for all words, and we're using topological epsilon machines to infer this, the only machine that's in there that has full support is a single state 0, 1 for binary alphabet. So it will collapse down to that thing. There is nothing that is like a first order Markov chain. So you want to add that. And again, we don't have to use this set, but that's what we're going to use for the first one. It's very structured. And so even in this more restricted set, the numbers grow pretty quickly. So this is one of the tables, or part of one of the tables from Ben's paper. And it gives you a sense of, this is the number of states. So 1 state, 2 state, 3 state, 4 state. This is the number of edges. And the number up here is the total number with 1 state, total number with 2 states, 3 states, 4 states. And then it's divided out here by, there's, for example, 3 states and 3 edges, there's 2 of them. 3 states, 4 edges, there's 22 of them. And these are full alphabet, which means that these machines must produce both a 0 and a 1. So for example, the machine that has just a 1 edge and gives that 1 is not in here, things like that. So just in terms of the sheer numbers of candidate topologies, this is what you get for topological epsilon machines. Yeah?
Can you repeat what you just said about it having to show both the 0 and the 1?
Yeah, so that's what, in terms of the numbers, that it means being a full alphabet topology. It means that there's not in this set, so that, for example, there's only one state machine. It's the one that has a 0 and 1 and comes back to that state. There's not a machine that has outputs of 1 and just, it's just like does ones.
What alphabet? Are we working strictly with binary?
In this case, I'm going to be doing binary examples. It doesn't have to be, but yeah. So in this case, it's, but if it were more than that, like if it were 3 letters, you would, if it's a full alphabet thing, it would still have to be, it'd have to put out 1, 2, and 3 as the symbols.
But the numbers on there wouldn't change based on
Oh, no. The numbers, yeah, I'm sorry. So the 2 means alphabet size 2. I'm sorry, yeah. So this gets much worse as the alphabet size gets bigger, yeah.
So it's the the 2n minus 1 pattern for the number of edges, does that come about because you have to have equal probabilities of...
Right, so there's all these restrictions that you can't have. You have to have probabilistically distinct states when all the outgoing edges are equally probable. That puts lots of restrictions on what you can have there, yeah. Okay, so that's the set. And then something that we're kind of talking about, and I'm not going to belabor this, but I wanted to bring out this idea that the way that we're thinking about epsilon machines, and I think most of what you've done has been thinking about the history formulation of epsilon machines, and this is the idea that you have a process that determines the epsilon machine structure through an equivalence relation. So you group equivalent histories if they have the same future morphs. And there's another way to think about this that's been employed by Nick Travers, who's finishing up his PhD now. And there's a whole series of papers that were related to synchronization and actually the equivalence between these two different viewpoints. And the other viewpoint is that a generator formalism for epsilon machines, and it turns things around. An epsilon machine defines the process that can be produced by the topology. So in a certain sense, this is more the way to think about the inference that we're doing here, in that we're going to look at try and infer a bunch of generator epsilon machines that are consistent with the data that we've seen. We don't apply an equivalence relation or anything like that. It's going to be much more in the style of this way of thinking about epsilon machines. Okay. So how do we go? So it's Bayes' theorem again. And so, I mean, even the symbols all change, but it's the basic idea should be familiar at this point. And again, we're going from a prior, so we're going to have to specify a prior. We're going to choose our set of candidate models, which I use as script M, and we're going to be using topological epsilon machines. But you can choose whatever set you want. And you have to have some sort of prior of MJ is going to be a particular member of that set. What is the probability of that a priori? And then there's going to have to be a likelihood-like term, which is what is the probability of that data given a particular topology. And really, we're using stuff from earlier on, from the probability of the data given a single topology. So we actually calculated these things in the previous lecture. And this value actually really doesn't depend on the set that we're considering. So we're writing it this way just so the patterns look similar, but really we've calculated this thing previously. And the idea, again, is that we want to update this prior to a posterior using these weights. And the normalization term, again, is basically just summing the numerator over all things. And so just like every instance of Bayes' theorem where the thing you're trying to infer is discrete sets of objects, you're doing this sum normalization term. The only time that we've done something more complicated is for the transition probabilities, where those are continuous parameters. And then we actually had to do integrals over multidimensional simplices. That is more complicated. This is pretty straightforward and very similar to lots of calculations already done where you have a probability and you're renormalizing it based on some context. Okay, so what kind of prior will we choose? And this is just one prior. I think it's fairly effective, but I'm sure I could be convinced that there were other ways to do this. What we're going to do is use a simple prior that has a single parameter. In this case, it will be beta. And there's going to be an exponential penalty for some function of the model topology. So in this case, what I'm saying here of f of mi is the default in Campy and in the code that you'll be able to play around with is just to count the number of states. And so there'll be an exponential penalty for the number of states, and it'll be weighted by this beta value that you set. You could make this the number of edges. It could be something else. And I mean, we can also set this to 0 if we want to. And then it's basically all of the things are just equally likely. Although there are some kind of Occam's razors effects on the lower levels in terms of the number of transition probabilities and how many states that will naturally prefer one topology over another. This is sort of an extra part. And actually for the topological epsilon machines, this becomes important for very small data sets because there are examples of, for example, there are periodic processes in there that will just have 3 states and they'll go 0, 1, 1. that's a weird structure because we're not inferring transition probabilities. They're all probability 1 by definition. Its likelihood is 1 or 0. And so even if it isn't really a periodic process, you can have that pop out and be very, very probable for small data sets. And this can remove that aspect of it. So it will give some penalty for the fact that you're giving a 3-state periodic process to something even though you only have 50 symbols worth of data. This becomes less important as you get more and more data, but in particular at small data sizes, and this is often the case for priors. They're much more important when they're small data, and much less important when there's lots of data. But so this is one way to do it, and the idea again is to sort of start off with the simplest model that you can, and let the data push it to something that actually can have high likelihood. All right, so what do we do? Yeah.
Is there a particular reason why we like just assume, to me, you can just pick, say, a 6 and do all possible labels and then just infer edge probabilities and then like eliminate ones that are approximately 0?
So say again,
instead of doing an enumeration, you just assume a really complicated one.
Sure.
And then fit
Yeah.
edge probabilities and then kind of
manually look at.
Right. Well, you can see that if you have a bunch of zeros in your transition probability.
Sure. Yeah.
Is there just, I don't know, is there a benefit over enumerating topologies versus?
Well, one is it. I mean, there is some power to. I mean, one thing we'll find is that for all of the examples, in particular, when we get to the golden mean and the even and the SNS, that when we use this enumeration technique, there will be thousands of unifidelity representations that accept data at 100. And so what you end up getting representing these things will be, in the case of the golden mean and the even, you get the correct topology with really high probability, and these other ones with much, much less probability. But for SNS, that's not in the class at all. And so it's representing, yeah, I'm not sure. I mean, I think it's not clear. I think there's some power to looking at the set.
So when you put a prior over, so you're talking about 6 states all connected to all.
Right.
So your prior is all transitions could occur, right?
No, we do what we did on Tuesday.
But it turns out there is this issue of the statistical significance of not having seen a transition. And the net result is it's very hard for these inference algorithms to actually completely turn off an edge. So there's actually a bias towards keeping a little bit of epsilon probability if you allow that to be in your prior, that this transition there. So the trade-off is to say we're going to step through topologies explicitly testing setting transition probabilities to 0. And that's really focusing more on the structural aspect. It's really the restricted transitions that mean you're looking at differently structured processes as opposed to some big multinomial process Markov chain over 6 states with small transition probabilities. So practically, the inference algorithm have a very hard time pushing probabilities to 0 with finite data.
By design,
so that pushes you over to some class of processes where there are no restrictions. So that's a very strong bias towards unstructured processes.
Yeah.
It's one of those you could start with some generic machine, run it through. If you get small value transition probabilities, enumerate. So you start with the big
to motivate a set of
and
topologies.
then move back down.
Yeah.
Cutting out edges, cutting out states.
Yeah.
I don't know.
I mean, any creative way to come up with a constructive set is good. I mean, and certainly the transition probabilities will never be weighted to absolutely 0. I mean, they just they approach that because you have this, posterior distribution.
More like computationally, like
sure,
is looking at all 4-state machines more computational, single, like 6-state with all edges.
No, I mean, all the examples in terms of code, I mean, they'll run on like 30 seconds on your laptop. So, but if you really think that there's a 10-state machine or something, then enumeration becomes really, So, I mean, there's a trade-off at a certain point. But yeah. There were other questions, or?
I mean, it seems like there are these block diagonalization algorithms that you can also write
to do what?
I mean, where you can, I don't remember what the algorithms are, but there are some ways where you can take a huge matrix of data where you have information and then try and block diagonalize the data and see if you can get kind of like sub-machines or something along those lines.
In terms of analyzing the structures that are left?
Yeah.
Um,
I'm not sure.
yeah, I don't know. I mean, I can't comment because I
So one
don't.
example of
Yeah.
this is in neural networks. People are interested in community structure. And
Sure.
There are various forms of competing concepts and algorithms for clustering a set of nodes in a network
Right.
as a community.
Yeah.
So
That kind of thing.
Right.
Sure.
But again, these all suffer from being able to prune out things that really shouldn't be there. So the approach that Chris is talking about is really very complementary to this. And
Yeah.
it's more focused on trying to see which structures, by which we mean turning this edge completely off or turning that edge completely off.
Mm-hmm. Mm-hmm. Mm-hmm.
And so you could start with maybe you had data from the golden mean or even process, but you assume it's a four-state, all-connected thing. If you do that, it's very hard to see that it's a two-state with you never see two zeros in a row. You won't get it, whereas this way we'll pick it up very quickly.
Mm-hmm.
You see, and I should say there's always this trade-off in this, right?
Yeah.
All these algorithms, you give them infinite data,
Right.
they'll do it right. So in a very kind of crude sense, a lot of the issue we're talking about here is just efficiency, data efficient, the use of the data efficiently, and can I get more interesting results with smaller data sets? There's
Mhm.
always this kind of trade-off, and here we're kind of doing some computation to help that, bring it down to smaller data sets.
So, okay. All right. Yeah. I mean, so these are all good questions. I think that it's yeah. So what do we do with this posterior once we have it? And again, we have a probability of each topology given the data and the set that we've considered, whatever set we've chosen. And this is a normalized thing, so there's a variety of things that we can do in terms of using that. And I think the way that I would tend to use it, but again is more computationally intensive, is to use the whole posterior over all models. And I'll go through some algorithms of this, but we can quantify the uncertainty in structure, as well as quantifying the uncertainty in start state and transition probabilities that we did in the previous lecture for an individual topology. And then when we estimate things like H mu and C mu, it's taking into account uncertainty in structure, uncertainty in start state, uncertainty in transition probabilities. And another way, which can be okay and sometimes might not be, and I'll show you some examples where that's the case. So like SNS data is one example where this is dangerous, whereas you just take a single topology that is the most probable in the posterior. And so if this topology has 99.9999% in the set, probably you're okay and will still reflect the uncertainty. But if the most probable is not very likely in the set that you're considering, then you're really not capturing all the information that you have from the set. So this may not be a good substitution. So it's good to at least think about using the full set if you can get away with it. And that motivates two kind of pseudocode ways of thinking about how to sample from these. And this is, if you want to take n sub s number of samples, you would sample a topology from the posterior over your set. Then given that particular topology, you would sample a start state. Given that specific start state, you would use this to sample a set of transition probabilities, which is effectively an epsilon machine. And then you can evaluate any function. So this would be like our H mu or C mu. It could be transition probability. Well, transition probabilities don't make sense because they're attached to a particular thing, but functions, H mu, C mu. And then you'll be able to estimate whatever quantity you want. And each of these posterior distributions come from the various levels that we did. These from the previous lecture, this from today. And then the other is to just use the single maximum a posteriori topology, where you take that single thing. There's no longer the sampling of topology, but you still could sample start state and transition probabilities to capture some of the uncertainty and evaluate your functions. And even less refined is you could just take averages over these things and have sort of like one topology with an average transition probability averaged over the uncertainty in start states. And so there is a method to do that in Campy, but be careful if you use it. Word to the wise that it's at least good to think doing this is reasonable.
And just to emphasize the obvious, sample here is not the data.
No. Yeah. No, this is a sample of the function. So this is, okay. Yeah. No, so I mean, these are all distributions. So it's like I sample a number from a Gaussian distribution. Here I'm sampling from the posterior. Like this is on the previous slide. I wouldn't even have thought that that would be, but so that's part of the point is that this is a distribution and it's normalized. So I can sample from that thing, topologies. And that's what I'm doing. So here I'm literally sampling, give me a topology that's random XOR-like, because it was highly probable. And then given that it's a random XOR topology, sample a start state. But this start state depended upon the calculations we did in terms of how likely were the different start states given our particular data set. So this is one single data set in here. And all of these posterior distributions have been shaped by the single data set. So the samples are with respect to posterior distributions at each level. Yeah.
So the function that you're calculating, is that related to the function that you used in your prior, or is it?
No. In this, I mean, this is a general, you want to estimate entropy rate, or you want to estimate CMU or any of the quantities that are related to the epsilon machines, this would be the function that you have to give it an epsilon machine to calculate. And you need to sample all these things to get a particular setting for the transition probabilities. And so it samples in that sense of structure, start state, then transition probabilities. Then you actually have a Mealy HMM or a recurrent epsilon machine in Campy, and you can say, give me the entropy rate. And I'll give an example of this, so, which is exactly the next thing. So here's a practical example of doing this with something that we've already seen. So we're going to infer the structure of the EvenOdd process. And this is straightforward application of what we've just been talking about. So again, I'm going to declare the EvenOdd process with slightly strange transition probabilities just to make sure that it's not like the prior. So 0.1 and 0.9 and 0.3 and 0.7. Do that with a string. Use Campy to make an instant of it. And this is what it looks like. And so this is going to be what's going to be generating my single time series. And then I'm going to feed this to the algorithm and say, let's infer the structure, estimate entropy rate, CMU, these kinds of things. And so this is exactly what you get to play with in the second lab on stage. To do the inference, we have to do a couple of things.
How big a data set?
How big a data set? I will show. I mean, literally this is all executed. Yeah, so yeah. I think I did 5,000 samples in this case. But so yeah, all the code is shown. So first I'm going to just actually look at the prior over these things and not even look at the data. So we import the Bayesian stuff, and this particular library generator function is an interface to Ben's algorithm for enumerating structures. And so what this command does is says, give me 2 is the size of the alphabet, so all binary machines with 1, 2, 3, 4 states. And so that's assigned to this model set 1. And now I'm feeding this to model comparison EM. So last time we were doing infer EM, it was for a single topology, but now this is a different class. And instead of feeding it a single topology, we're setting a whole set of topologies. And then I set my beta, which is the penalty for structure size, and this little tag verbose true actually spits out this little summary. So if you were to run this, it would say this as it's calculating the things. And so because I didn't feed it any data, notice I didn't generate any data and I didn't give it anything, this is just the prior over these model structures. And so that's what it says here, is it says that beta is 4. It says, well, there's 1,474 candidate machines. They're all possible because there's no data to eliminate any of them. A priori, they're all possible. Yeah?
Leaving the prior function
Yeah.
thing the same, if you just use beta as a parameter, are there any interesting dynamics that come from that, or is it pretty straightforward?
No, I mean, I think that what you set this to, for example, influences whether or not you approach CMU, estimates of CMU as a function of data size length from above or below. So this particular value is, at least for binary machines, is good for approaching CMU from below. And that's particularly important because the way the number of machines or candidates grows with size, so like you have many, many 4-state machines, so there's lots with high CMU. So if you want to start from below, you have to have a higher penalty. Yeah. But I mean, in the way that I'm applying it here, this is just something that you set, and it would be your inference would be conditioned on that. If you want to add another level, you could actually, put a prior over that and let the data tell you which is the best beta, right? So I mean, this could be done endlessly, right? Yeah. So, okay, but so no data here. And here we're going to pull out. I'm using MAP. Usually that means maximum a posteriori. In this case, it's actually a priori because we haven't given any data. I'm just saying what is the most likely machine without any data given the prior that I've set. So that's what I do with this particular method. So I use the prior that I declared, and this does what I was saying, which pulls out the most likely and then just averages over the uncertainty at start state, which for a single state thing doesn't make any sense, but it gives the posteriors. And what it gives you back is the single state machine with 50-50, and that's because with a penalty for structure size, that's the most likely a priori. When we feed data this, our prior distribution will be updated to a posterior distribution, and when we call these same things, it will be different because the data is restricting what class of things we can get. Okay, so that's what we do next. So yeah, here I actually generate the data. So I say 5,000 symbols, and then I set up my posterior. It looks very much like setting up my prior. Again, I'm doing binary 1, 2, 3, 4 state machines, and now when I set the posterior, I feed the data in, and I use beta equals 4 and verbose is true. And now when we run this, the output says, well, I considered all 1,474, but actually only 175 of them were possible. And what that means is that for the other ones that are not included, every start state in that topology was tried. It went somewhere through there, and it came to a node where it required a particular symbol, and it wasn't there. And so it just said, plunk. So, but there are 175 options of what could be viable topologies. Okay. And so then when we actually want to look at, again, just a single representation, because I will look at sort of estimating CMU and HMU in more general form, but if you want a single representation of the most likely object, again, we can get this. It gives me the maximum, in this case, a posteriori topology, and it gives me averages over uncertainty in start state and gives me the posterior means of the transition probability. So it gives you something to look at. I mean, in this case, even with 5,000 symbols, it's actually quite good. So this is the original data source, and this is if you run Campy, it will pop back at you if you just say draw this thing. And so this actually is deceivingly good. I mean, 5,000 data points, this is a fair amount of data. But for that amount, it would not be unusual to see this to be 0.32 and this 0.68. So there would be some kinds of fluctuations. But again, there are tools in here where you can actually sample over all that and say that it's this particular value with this amount of uncertainty if you really want to get to that level and do it. But the point being is that it captured the correct topology. I think we all agree and see that it's the same? Yeah. Yeah. I guess the default in when you declare EvenOdd, somehow it does this nicely and not this one. I don't muck with the Campy settings, but this is what you would get if you just ran it in Campy. But so it does a good job there. What if we want to do something that's closer to what we were doing last lecture, which was to estimate CMU and HMU? But now we're going to use the set of all topologies that we used. We're not going to just use one. But this code should look, if you look back at the previous lecture, will look exactly like what we were doing for a single known topology, except what our priors and posteriors are now over whole sets of topologies. But they're these same methods that look and can be used in similar ways. But what's different here is, so we're going to do, again, what we did at the end of last lecture is we're going to use one loop to sample both from the prior and the posterior, and we're going to estimate HMU for the prior, CMU for the prior, HMU from the posterior, CMU from the posterior each time through, and then add them to a list. But this prior now is over models, and this prior is over models. So now the machine that gets spit out each time could be different, and will be different some of the time. So when you calculate these things, CMU and HMU will change in ways you can't with a single fixed topology. So this is generate sample does the first algorithm that I was listening to you, which was sample from the posterior over model topologies, then sample a start state, then sample a set of transition probabilities, and that's what's returned here. And so actually the node, the start state here, is what's the start state that was sampled, if you wanted it. And so we're doing all of these at the same time, and we can, again, look at what these look like. And again, some of this is hopefully for people who want to use this for projects, useful code, in that we're going to feed this then to histograms. So our prior samples, posterior, we're going to make blue and green and print them. In the worksheet on Sage, I've also done the finding the mean from the samples and the credible intervals, just the way that we were doing before. I don't have them in the slides here, but they're on the worksheet, so you can look at that, which will give you like a mean of entropy rate and a mean of CMU and kind of error bars or credible intervals. But if we just plot the samples, the blue is the prior, and the green is the posterior, and the true value, if you use the thing that we put in the beginning, is 0.438. And so it does a good job of capturing that. And the one thing that you should notice from the prior is that all of these structured processes, so the only process in the topological epsilon machines that can actually create these really high entropy rates is the single state two-edge thing. Most of them can't get higher, and we saw that last time with looking at just the EvenOdd process, that the maximum entropy rate you could get was somewhere around 0.6. So the fact that a priori you see this broad uncertainty in entropy rate is a function of the fact that that single state machine is in there. The fact that the posterior is peaked like this means that the single state is not very likely anymore once you've fed the data to it. Okay, so that's entropy rate, and again, I'll just go through these a little bit quicker, but same thing for CMU. We're just going to take the samples that we created a couple of slides ago and look at what those look like. And this is harder to see, and I'll show it another way, but the CMU, because of the prior, when we know we pulled out the single state as the most probable thing, and so this big peak here is single state, it has no CMU. This little peak here is log 2. So it's the two-state machines. There's a little blip here. That's the log base 2 of 3. And you can see that better in some of the things that I'll showing up later. But there's this decay in sort of structure that's a function of how we set beta and what set of models we looked at. But then the posterior pops out the one that is actually good after looking at the data in a statistical sense. And the true value is 1.84. And again, this ends up being a good approximation, and partially that's because it gets the right topology, right? And the transition probabilities are defined well enough that CMU comes out good. Okay, and so again, we can look at CMU and HMU together, and I think this is a useful thing to do, and I've just been doing CMU and HMU, but that's for each of these samples. We look at the CMU and HMU that came from a particular machine for each one of those samples. And so the blue, again, is the prior, and the green, this little spot here, is the posterior. And so this whole line here is the single state machine with different transition probabilities. So when you're sampling from the prior, you're just seeing, oh, it's more likely to get the single state machine, and then it gets a certain set of transition probabilities, and it basically all these samples are single state. And then this is CMU's 1 is two-state machines, and these are different settings for the transition probabilities on sets of two-state machines. And if this is only 2,000 samples, so to really fill this in, you need to do larger numbers of this. But you would see more and more of this. If I were to set beta to 0, you would see something that was not much here and a huge cloud a priori up here. So this is part of how you decide what beta to set. And I'm taking the approach, I want structure to prove itself through data. And that's basically what this beta setting is doing. And the green is then, once the data is applied, lots of topologies are ruled out. We have probabilities for each of these topologies, and there's start states and transition probabilities. We sample all these things, and most likely it looks like it's probably just sampling this one structure most of the time over and over and over again. That's not always the case, and we'll see an example of that in just a second. But it gets, the entropy rate is 0.43, and 0.18 is the CMU. So the samples are focusing in on the right H mu C mu combination. Yeah.
Question. So if you had set beta very low and you had this big diffuse cloud, how do you expect the posterior would look? Would it be more spread? Or would it, in this case, with the limited samples and everything?
Yeah, no, my guess is that it would look really similar. With partially, it's a function of how much data you provide to the posterior. So the fact that we gave it 5,000 samples, my guess is that this would still be a posteriori very likely, and this posterior would probably look very, very similar. If I had only fed 200 symbols to the algorithm, then they would be closer and they'd be much more diffuse. So it's a function of what models you set, how you set your prior, and then how much data you give the thing. So the more data you give, the more likely the posterior is to be different from the prior. So yeah, that's a good question. And that's part of the reason that I like visualizing the prior and the posterior, is to get a sense of, is this capturing the kinds of things that I want to actually capture? Okay. So now just to give you an example of some of the processes that you know without the code, but just to give some figures. And this is going into the paper that Jim and I are working on. What I did is I took a single time series for each of these processes of length 2 to the 17, and then I analyzed substrings of that, of length 2 to the I for I is 0, 1, 2. So length 1, length 2, length 4, length thing. So basically, I'm going to have this long time series, but I only look at the first symbol, then I look at the next 2, then I look 4. And each time I'm, say, taking those 4 symbols and pushing it into the code, what does it give back to me? Then I do it again for length 8 to just give a sense of the convergence. So partially that might actually get to sort of how the posterior changes as you get more and more data, and really reflect on the earlier question. And so in this case, I'm using all 1 to 5 state binary topological epsilon machines. So that ups it to 36,660. I'm using beta again of 4. And in this case, I'm sampling for each of these L's. When I look at a substring, I'm sampling to estimate H mu and C mu 50,000 times. So I get a good sense of what the actual posterior looks like, and prior. And we would just want to look at the patterns of how this converges, and in particular for different processes, what is happening. All right, so the first thing is to look at the prior. And so this kind of looks at what happens if you give different betas. So this is, I'm feeding no data to it, but I'm changing beta from 0 to 2 to 4. And the things to look at is, so these are the samples in C mu and H mu space, and then, for example, this is C mu this way. If you project that, marginalize it just on C mu, this is what the densities look like for those samples. And if you project this way, this is what the density of H mu looks like. And so one thing that I have done also is notice that I'm doing logs of 1 plus the probability, because some of these are quite different in scale actually, and the plots just are really difficult to see. So some of these differences are actually bigger, but you want to see certain patterns. So one is that for blue, what we already know, that's a big penalty for structure. A priori, we have a very big preference for C mu is equal to 0. That's that single state machine. And we see a peak at the 2-state machines, the 3-state machines. But if we decrease beta, that preference, then you still see a small peak at 0, a peak at 2, a peak at 3, and now it's much more of the mass in terms of the average structure in C mu is up here. And with beta equals 0, not having any penalty, now it's really pushed up that way. And that's partially just because there's so many machines that have that number of states. Yeah.
That's what I was going to ask.
Yeah, really, that's what's going on. Yeah. So, I mean, partially these differences are a function of the set that we chose, that we're being enumerative and we're choosing everything. So we want to have beta be careful in terms, and yeah, we just want to understand what the behavior is. H mu is less unusual, and the one thing that you can see is that with beta equals 4, again, we get this single state, so you can get the high entropy rates because a single state machine is there. And this is pretty much a function of that's very probable. Whereas if you don't have as much penalty, then you get this sort of peaked thing. If you just randomly sample all 1 to 5 state, topological epsilon machines with certain amounts of penalty, you get this peak of entropy rates, taking into account uncertainty. Yeah.
What was your penalty, like, specifically again? I know, like,
Is an exponential, like it's an e to the minus beta times the number of states in the machine.
Just numbers.
Number of states, yeah. In this case, it's just number of states. Yeah, and so you end up getting these two patterns where actually the difference between 0 and 2 is not all that dramatic. With beta equals 4, entropy rate, you really see the single state machine coming out. So that gives you a sense of what happens without any data, without any restrictions by actually observed things. So let's feed it golden mean process data with beta equals 4. So this is with beta equals 4, and maybe I'll just go back quickly. So what we're comparing with the prior looks like the blue thing here. So it's very strongly this here, and then a little bit of stuff up here, this blue pattern, and this blue pattern. So we're comparing that once we feed the data. This was just to give you a sense of how the prior changed with different beta values. The actual examples with data, I'm now choosing this one, beta equals 4. And so in this case, L equals 1 is black, so basically we just get the prior back. L equals 64 is the brown, and then L equals 16,384 is blue. And the general pattern that one should see is that as you go from black to brown to blue, is that you're converging in H mu and C mu space. And actually, so these dashed lines are the correct values for these things. So correct values and correct values. So by 16,000 symbols, you've, in this case, certainly identified the golden mean structure, and you're estimating C mu and H mu with quite a bit of accuracy. And probably that shouldn't be super surprising because the topology is in the set that we're considering. So it should do this. So we can look more generally at the convergence kind of things. And so what I'm doing here is now looking at each of these substrings. And again, I was sampling and looking at the density as a function of length. So let me look at C mu in particular. So this is a sort of a slice as you get from very small amounts of data to very large amounts of data. And the vertical is the posterior distribution. There's a dashed line is the true value. And there's a little gray line that you may or may not be able to see that winds in here, which is the posterior mean for C mu. And so the fact that I used beta equals 4 means that the estimates are very small and then converge to the right thing. But it also shows that, in particular, for sample sizes that are not that large, this is a multi-peaked thing, and it's not at all clear for C mu. There's ambiguity in the structure. And entropy rate here, again, we have this broad distribution at very small data lengths, and as you get more and more, it converges to the right value. And so this is the full data set, and that's basically the prior at the beginning in both of these cases, just looking at H mu and C mu. And so this is an example of a very nicely converging thing where, so like to the 10 right here, this is only 1,000 symbols. We've already converged pretty quickly.
So as we think about it converging as we add data, we explored all the difference between having, like in this case, an uninterrupted string of data as opposed to multiple shorter strings. Since in the case where
it makes a difference,
right, you have the added advantage of like being able to weed out just things that can't match that long string.
Right, yeah, definitely. It makes a difference. So if I do one long string, I basically only have to worry about inferring the start state and the hidden state path once.
Right.
But if I'm really going to apply this to, data set 1 and data set 2, and data set 2 is really sort of, there's some unknown amount of time and dynamics in between the two of them, I would basically have to do the same thing over again. One thing I could do is do the first inference and get a posterior, make that my prior for the next data set, but I would still be inferring start states and all these kind of things. So, but you would still get the benefit of increased amounts of data. But yeah, partially this is just one string of data. But yeah, so that is a real, you have to think about these things. It's a good question. All right, so even process. So, I mean, I guess one thing to say is that we're sort of going in increasing complexity. So the golden mean is the states really correspond to something that is observable. It's a first order Markov chain with a restriction, basically. Like you could know that one state is really, there's no ambiguity. Let's be clear about this. You know, because you put a 1 going in here and a 0 going in here, this could be identified with having seen a 0 and this with a 1. Even process really ends up being something that is an extra level of complexity because we no longer, there's whole groups of histories that these correspond to, and there's not a one-to-one correspondence. So in principle, this is much more complicated. And I mean, certainly in previous work that Jim and I did, we used just sort of first and second and third and fourth order Markov chains to infer things like this. And there you would see that you needed higher and higher order Markov chains to approximate the even process as you give it more and more data because it can't be captured by a normal Markov chain, whereas the golden mean can be captured fairly effectively. But now we're dealing with a model class that can capture it. And the same kind of coloring as we had for golden mean. And actually, this ends up looking really, really similar to the golden mean in all of the patterns. Again, the true values are the dashed lines. This is entropy rate and C mu. And again, for basically the prior, for 64 symbols and then for 16,000. And I mean, I guess the details of the bumps in structure and these kind of things are slightly different because different sets of topologies are being ruled out. But overall, there's a strong convergence just like we had before. And again, this model topology is in the set we're considering, so we would expect it to converge. And it does by 16,000. And if we look at these convergence plots of C mu and of H mu as a function, again, from prior to posterior and prior to posterior, you get a good convergence. And I mean, one thing I like about these also is that I'm using a single data set and I'm just looking at substrings. So I didn't do like average golden mean behavior or average even process behavior. I just literally generated 2 to the 17 symbols and then I chunked it, did the analysis, chunked it, and all this. So you get a sense of this convergence, and you could do this with a real data set, right? You don't have to know what it is.
I'm just wondering, the more complicated behavior early on, is it because it has a higher Markov order in the even process? Like in the lower, for H mu?
For H mu?
Yeah.
I don't know, is it more complicated? I mean, yeah. A little bit, yeah, I mean, I'll get into sort of the number of accepting topology, but the details of exactly how these things are being weeded out, I think, is still something we're looking into. But certainly there will be differences in terms of, I mean, they're different languages. I mean, the support is different. Yeah, so the convergence is potentially non-trivial. In some ways, it's amazing that they're as similar as they are. So for the last one now, an example of something where SNS is non-unifilar. So like I could not include this and feed it into my algorithm because it just can't find state paths. It would get to this point and it would go, I don't know where to go. And that's where the other algorithms, like the expectation maximization work, is they're doing this optimization over path.
What does simple mean?
What does simple mean in terms of the?
Just in terms of definition.
Smallest one I could find was interesting.
Yeah.
Okay, like not a vocab.
No.
Historical.
Yeah, it's one of these sets of typical HMMs that we're looking at as data sources to consider how different things work. Yeah. But this is interesting for us because this is not in the set of models that we're using. So what does this thing do? And so in this case, you can calculate the entropy rate. So this dashed line actually is the entropy rate for SNS. And surprisingly, this actually does get the entropy rate. And this seems to be a pattern that happens in a lot of cases where even though the models that are in the set that we're using, the data source is not in there, it's still capturing the entropy rate. And of course, it can't capture structure, and we see something extra complicated. And even for the large data sets, and this persists all the way out, we'll see that in a second, is that this really is two peaks in C mu. And so when you actually look at the details, there's actually quite a few topologies that are all on the order of like 5 or 8% probability. And so there's like a set of 3 that are all together and another set. So exactly why that happens, I mean, partially it's out of class. But this is certainly non-trivial behavior, and we can really see that when we look at the convergence of these things. The behavior is much, much more complicated.
I was thinking about that. Does that mean that maybe you can create 2 epsilon machines and then create another one that samples between the 2 epsilon machines?
Right. Yeah. I mean, you could elaborate on the model class. Certainly, yeah. I mean, I'll do an example at the end of lecture where I do exactly that, where I take a data set of one process and then just add another process on the end and see what you get. But in this case, yeah, I mean, it's just completely out of model class. And the entropy rate actually, I mean, it doesn't look too different in terms of convergence from even and GM. But where it's really, really different, and the more you look at the actual specifics of the details, it really is different, is that you have this very complicated increasing trend as a function of data length for C mu, and you end up here with this thing that's very multi-peaked. And it isn't, again, this isn't just, even though there's 2 peaks, it's not 2 models. It's quite a few models that are actually making this up. So, I mean, one interesting thing is, are there ways that we can, are things like this typical of out-of-class examples? And I mean, certainly for cases where you're out of class means that I have 10-state unifilar HMM and I'm only using 1 to 8 states, I'm not sure that you're going to get this kind of signal. So out of class, I don't think necessarily will give these complicated things. It won't. I'm not sure that this will actually be a signature that out of class is happening. So that's, I think, a very not simple thing to figure out. But in this case, it gives a very complicated behavior. And so the one thing that goes towards answering some of these kinds of things is just looking at the number of machines that accept the data as a function of data length. So this is starting off at the beginning, this is the starting amount of all 36,600 machines. And then this is the subsamples that we look at. And we're saying we give this data of length 1 or length 4 or 2 to the 4. How many machines will actually have a path for some start state? So there's some start state where the machine will accept the data. It won't come to a node and have a symbol that it needs to produce and then just get stuck. And the common pattern here is for GM, for even, and for SNS is that in the beginning, of course, everything accepts, but then there's this bend down, and by 2 to the 6, you hit this lower bound where the support is similar, and the GM and the SNS are exactly the same. It's 6,225 of 36,600 will accept SNS data up to 2 to the 17 data, whereas for even, there's less. And so, I mean, part of this is a function of, in particular for golden mean even, it's easy to see how you could take a 3-state machine and bury a 2-state even inside it. And so it would just rattle around in those 2 states. And then there's more elaborations with it. It's less clear how SNS does that, but certainly the fact that the support of these 2 things is similar means that this is very much, of course, driven by just not so much the probabilities, but just the support of what's going on. So that's where the interests of Ryan in sort of automata and these kinds of things, I think, will come in handy, trying to figure out what's common about the languages of these things related to the actual data source. Yeah.
How many of these are just random coin flip processes?
Well, so that will, yeah.
They would always be.
Well, so that's the interesting thing is that, yeah, so because they're topological, there's only the single state.
Okay.
2 edge, yeah. So it's not all, yeah, that's the only coin flip in there. That's the only full support, yeah. Everything else has some sort of restrictions.
Okay.
Yeah. So it's much less trivial than you might think, actually. Yeah. So interesting and to be investigated.
That is one of the benefits of the topological machine.
Well, right, they're very structure full, in a certain sense, yeah.
You don't have a bunch of coin flips.
Right. Yeah. Okay, so then I wanted to just kind of finish with a couple of fun examples, and again, these are in the Sage notebooks, of things that you might run into. So I just came up with a couple of things that might be problematic. And so one is the true model topology, as we've already discussed, might not be in the set you're considering. And certainly that's true for S and S. But I'll do an example where we do the even and odd, which is a 4-state machine, but only allow 1 to 3-state machines. What do you get back? That's an interesting thing to think about. And then, what if it's non-stationary? The transition probabilities or even the structure change over time, or if this is in space, over space. What does the resulting inference tell you? And I guess one of the things is that when you get to dealing with real data, you want to, as much as possible, have secondary checks in terms of if you have measurements from a real physical system, you come up with these models, you want to check predictions, what does your model say about the physical system, and make sure that these all make sense. And there may be ways that don't come out of the statistical modeling to rule out particular kinds of things. And those then can be implemented as reducing your set of candidate models or restrictions in terms of the priors that you're setting, all these kinds of things. But just 2 examples of what could happen. So the first is just not enough states in the set. So the code, again, is the same thing, except now we only have 1, 2, and 3-state topologies. And we're going to give it the EvenOdd data that we generated before. So it's exactly the same data we did before. But we now don't have the correct topology in there. Otherwise, we're using beta equals 4 again. And now when we run it, we see that now there's only 86 topologies in the 1 to 3, and 10 are possible. And again, we pull out what is the most likely one. And again, most likely, and then averaging over start state and transition probabilities. You end up getting something that looks like this. So true topology that generated the data with the right things. This is the best model in the 1 to 3 states. And this is actually, I think when you look at the notebooks, I was playing around with it this morning, this is 99% probable in the set that you've considered. So that doesn't mean when it's really, the posterior probability is high, it doesn't mean it's the right model necessarily. It means it's the most probable in the set you've considered given the data you've provided. So that's kind of the lesson I'm trying to push here. Yeah.
So if we were to run it compared to what the probability is when you do 1, 2, 3, 4, how does that compare? Like, what's the probability of that given the same amount of data when you have 1?
Oh, I think that in terms of the correct topology in that set versus this one, that one's also high, but I think less convincing. Partially, there's more options for that length, but I mean it's high. You can check on the notebooks actually. It's really easy to print it out. So I'm sure it was not 99% I think for the other one as well. But I mean there's certain things here where somehow there's certain elements of this part here that are averaging over aspects here. I mean, you can see the 0.3 and the 1 and the 0.7, so you can see it capturing particular parts of the process, but somehow it's averaging over other parts of this. And so certainly the data that was generated by this could be generated by this, and with similar probabilities, probably, but I mean, yeah, it's interesting to see how different they are. Yeah.
But at the same time, pretty close, because
Right.
if you look at B feeding into A, there's a loop there, and you get rid of that loop, like you just skip that step and just feed back into like 0, which would be, I mean, in my mind, what would be A. So, I mean.
Yeah, I mean, it should be really, really similar.
Like,
Yeah.
Is that loop, I mean, the loop's relevant, but it's just an extra step because you know you're going to end up back there.
So, I mean, this is the best that the set of models that we gave could do. But if you include the correct topology, it will give back the thing, and it sees it as.
What happens if you do 2-state?
That ends up only being, yeah, I don't know actually, but you could try it. It's really easy. It will take 2 seconds of computer time. But yeah, I mean, it ends up being these kind of averaging over. I mean, it's describing the statistics on some sort of average sense, and I think that also will be shown in the next example. But yeah,
Question, I guess.
Yeah.
So notice that looks like there's a really small probability of getting a single 1 after a 0. That would actually go
In the real one?
in the inferred one.
In the inferred
real
one.
looks like there's a decent probability of just getting 1 instance.
Yeah.
But so I was wondering if maybe you always kind of make some sacrifice like that, like some general thing always gets kind of thrown out. It looks like it really does really bad at that, but good at everything else.
Yeah. I mean, almost inevitably it has to do something like that if it doesn't have the right structure. It's going to, I mean, the fact that we get this structure back just means that there was a path for some start state for data that comes from this thing to go through here. And if you want to, like, you can go in and you can look and see which of these possible start states were possible, and what their probabilities were and all these kind of things. So yeah, there's a lot of interesting things to be thought about this, I think. And then
Another question too.
yeah.
So it seems like there's a trade-off, right? If you have a binary string with this particular machine,
Uh-huh.
or if you have like a 3-word, or not binary alphabet, and then you have a
Right.
3-word alphabet,
Uh-huh.
where your third word is actually 1-1 or something, right?
Uh-huh.
Because it seems like you've got that one loop between C and D,
Oh, I see.
where you got just, it's an extra word, basically, a 1-1. And if you assume that, right, if you assume like a ternary alphabet, 1, would you run faster? Would this algorithm run faster? And or 2, would you you'd be able to capture that with a 3-state system, I assume, right?
Yeah. Huh.
Yeah, between alphabet size and states. Yeah.
Right. So, I mean, I think that, yeah. Yeah. Right, your string is still a binary string. So, I mean, you could do all kinds of weird things with this. I mean, I could actually take a binary time series and use a library generator for all alphabets for the alphabet of size 3, which include 1 and 2 and 3. And there would be lots of machines that would accept that, and they would only go on the 0, 1 edges, and it would just not use all these kind of things. I think that it's like when you know what the answer is, and you have an answer. I mean, it's easy to engineer after the fact how you could do this better. But part of the point that I'm making here is that if we really didn't know that this was the true source, and for whatever reason we could only use 1 to 3 state machines, we were just limited by our computer power, this would come back, and it would be really the most probable. So it's just like the words of warnings. It's I know some of the postdocs like to call this Bayesian magic, but I don't think it's magic. I mean, it's really, really straightforward and like very empirical. It does the best it can with the data you've given and the set of models.
So like with your assuming non-universal source that capture H mu
Right.
really well.
Right.
Is that just kind of general because it is, this is encoding your, you can calculate H mu from your
Right, from
time
strings.
series.
Right, yeah, less model dependent in
less
some
model
sense.
dependent.
Yeah,
So
yeah.
in that sense,
Yeah.
H mu or things that don't depend on the actual states are
Right.
probably more reliable from your inferred machines.
Very likely, yeah,
And-
yeah. I mean, I can't answer with definiteness, but yes, I think that's very likely. Yeah.
Yeah, rather than looking at the like state entropy, it
Right, then it really depends on the,
really depends on
yeah.
the model.
yeah, definitely.
It's kind of more of a general question here to Jim also.
Mhm.
I mean, you can kind of define a metric, right? Some sort of like Hamming distance or something
Between machines,
between processes.
the trustees, yeah. Mm-hmm. Yeah.
So I mean, like, would you be able to compare like the kind of, I don't want to call it a Hamming distance, but between the strings that generate from the infer topology and the true topology?
Right.
Can you get a distance from that?
I mean, there are a variety of ways of doing that. I mean, my most naive thought would be initially to just sort of, I mean, you could look at the distribution of words. I mean, or the support first. So look at the support of all future words of length 10. And then there'd be a more refined thing of the probabilities. So you could look at some sort of relative entropy. And then others, maybe, I don't know.
This is a long-standing problem that's still open.
Yeah.
To actually do it right. Is as clean as you'd like it to be in terms of having this geometry in the space of processes? I think he worked on that last year's class. So,
Mm-hmm.
but you're kind of smiling. At your question.
Mm-hmm. Yeah. Yeah.
I've been
No, it's a good
offering
que-
my issue
excellent
for
question.
my final
Yeah.
project, but
Yeah.
We're still working on this.
Yeah. I mean, an extra challenging thing is, though, is that, I mean, you could think about doing this in the inference context of if you know the data source and you have an inferred thing of measuring this, but when you don't have the true thing,
Right.
then it's unclear you have to come up with some sort of secondary tests of this. So let's see, yes, not that much more time. So just a quick last example of something that I'm calling non-stationary, but a very kind of trivial but interesting, I think, at least to go through. And so all I do for this one is I create the golden mean topology, and I create the even topology, and then the first 4,000 symbols are the golden mean. The second 6,000 symbols are the even process, just tacked right on. So it just changes topologies in midstream. And so I only do part of this, but what you would typically do when you have a data set is just let's take all the data at once and let's see what we get. And so in this case, I used 1 to 3 state machines. You could use 1 to 4 or 1 to 5. I give it that data. Again, I use beta equals 4 that we've already seen. And in this case, I run 86 machines possible, but only 3 accept the data. And so again, we pull out the best one and average over start state and transition probability uncertainty. And we get something that looks like this. So the one thing that's interesting, I mean, this accepts that data set. There is a path through there. And you can definitely see elements of both processes in this. Yeah, I mean, it's definitely the even. Yeah. But so, I mean, part of the reason that I was thinking about.
Zeros on the top.
Yeah.
Never mind.
Yeah. So one thing that this, and this is actually the last slide, but I mean, one of the things that this motivates is that if you have a data series, and the underlying assumptions in this model is that it's a static structure. The transition probability is not changing as a function of your time series. That may not be true in what you're dealing with. So one way to get around this kind of thing would be to actually chunk up the data and look at the first 4,000, then the next 4,000, the next 4,000. And so I've done this, and actually what you'll get in that case is you'll get golden mean, golden mean, golden mean. When you hit a part that's overlapping, you get this back. Then you get to even, and it becomes even, 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 even. But there is then this question of, if those changes are really quick, that's much more complicated. And so, I mean, you can at least make these kinds of tests. In the notebook, I have this thing where I actually print out the hidden state paths as a function of the time series that's in the notebook when you look on Sage. So you can see that actually there's a difference, like 0 only happens in the golden mean part of the data set, as far as I can tell. And then it basically rattles around here. So there's a different use of states as a function of where you are in the time series. So yeah, fun things to think about.